So now we will be discussing about heap sort. So let me start with the fundamental question. What is a heap? At its core, a heap is a specialized tree-based data structure that satisfies a special property called the heap property. Right? There are two types of heaps. They are the mirror images of each other. Okay? In a max heap, every parent node is greater than the or equal to its children. This means the root of the heap contains the largest element in the entire structure. Okay? You can see in the diagram. So think of it like a hierarchy where the parents are always older than their children. The oldest person is at the top. So if you need the maximum element, you just look at the root, right? In the min heap, every parent node is less than or equal to its children. Okay? The root contains the smallest element. This is like a hierarchy where younger people are above the older people. So the youngest is at the top, right? So let me give you an example. You can see here both 20 and 30 and 70, the largest is 70, right? And from 40 and 10 and 60, the largest is 60, and from these two and this, the largest is 90. So you can see the max heap, every parent is greater than or equal to this element, right? Here in the equation you can see, right? So we can map the each node in a specific index in an array. Given an index I starting from 0, the left child is at index 2i plus 1, right? The right child is at index 2i plus 2. And the parents, we can say it's in index flow, right? I minus 1 divided by 2, right? So let me explain some terms, operations we will use in heap sort. Heapify. Heapify means the process of maintaining the heap property. Given a node I, we compare it with its children, right? Then we get the maximum or minimum. If it is the largest, it's for max heap, and we swap it with the largest child, and then recursively heapify the affected subtree, right? This operation takes O log n time in the worst case, right? And then the second operation, we can say the build heap. This is a process of converting an arbitrary array into a heap. We start from the last non-leaf node, okay, and then heapify nodes towards upwards, right? And the final stage is extract the max. This removes and returns the maximum elements from the next heap. We swap the root with the last element, reduce the heap size, then heapify the new root, which takes the whole log n time, right? So these three operations are the building blocks of heap sort, and the algorithm itself is simple. Build a max heap from the input array and repeatedly extract the maximum element, right, and place it at the end of the array. Okay. So here I will work through each step and explain why it does, right, and why it is necessary. The algorithm has two main phases: building the heap and the extracting elements, right? And step 1 is building the maximum heap from the input array. Okay, this is the first phase. We take the unsorted array, right? This is the array, original array, and what we do next, and we need to rearrange its elements so that they satisfy the max heap property. So we do this by heapifying each non-leaf node starting from last non-leaf node and working up to the root. After this step, the largest element is at the root, right? Here you can see, and we need to swap the root, which is the maximum, with the last element, right? Okay. In step 2, we now know the maximum element is at the root. We want to place this maximum element at the end of the array where it belongs to the sorted order. So we swap the root element with the last element of the heap, right? Here you can see, right? And what we can do, then we need to reduce heap size by 1. Okay, so we disregard this and heap size is reduced, right? And repeat these steps 2 to 4 until the heap size is 1. We keep extracting the maximum, place it at the end, and then reduce the heap size. After each extraction, we heapify the root. So we continue until one element remains in the heap. At that point, the array is fully sorted. Okay. So now let's look at some example. So this is original array 10, 4, 4, 10, 3, 5, 1, right? And this is the initial tree 4, 10, 3, 5, 1, right? You know how to fill trees, right? First we fill with left side, right? Then right side. After filling the same levels, we go to the next level, right? That's how we fill those trees, right? So we need to initially build the maximum heap. So what's maximum heap? Maximum heap is a complete binary tree where each parent node is greater than or equal to its children, right? For example, if a node has children 3 and 5, the parent must be at least 5. The important property is the largest element is always at the root of the heap, right? So we here heapify index, right? At index 1, the value is 10, right? So its children are 5 and 1, right? So since 10 is greater than the both of children, nothing changes. Okay, so then we heapify index 1, right? So then we heapify index 0, right? Now we examine the root. The value is here 4, right? The children are 10 and 3. Among these three, the 10 is the largest. Since the parent should always be the largest, we swap 4 and 10, right? And now the array becomes 10, 4, 3, 5, 1, right? So you need to continue the heapify, right? Now 4 has children 5 and 1, right? So 5 is the largest. We need to swap 4 and 5, right? So the max heap has been built successfully, right? Then the next step is we start heap sort. Now the sorting process begins. Notice that the root always contains the largest value So our strategy is simple: take the root, move it to the end, reduce the heap and rebuild the heap, right? So the root is 10, right? So swap it with the large element, last element, right, which is 1. Okay, now we have this one, 1 4 1 5 3 and 4, right? Okay, so here 10 is highlighted because it already needs final sorted version, right? So we reduce the heap size from 5 to 4, right? So now the remaining heap is 1 5 4 3 1 5 3 4, right? So the root is no longer the largest here, right? So we perform heap P5. Compare 1 5 and 3. So the largest is 5. So we need to sub 1 and 5, right? So now 1 moves to down, okay? And then next compare 1 and 4, right? So here 4 is the largest, so we need to swap them again, right? Now the heap becomes 5 5 4 3 4 3 1, right? So in the past two, again the root contains the largest remaining heap, which is 5, right? And now 5 join as a sorted section here, right? And we have reduced the heap size to 3. Now the largest element is 4 here, right? So we need to sub 4 and 1, right? So heap becomes 4 1 3, right? Now the root is 4, right? So swap it with the largest element in the remaining heap, right? So the 4 is the largest. Now we have this one, right? 4 1 3, right? So now 4 is in the correct position, so we added to this highlighted portion. Now we have 3 and 1 remaining, right? So we compare this. These are in corrected positions, right? 3 is already larger than 1, and the array becomes, now the heap contains only 2 elements of the root 3 with 1, right? So we have 3 here, right? And now we have, after that we have now only one element remaining is the heap. The algorithm stops, right? So the final sorted array becomes 1 3 4 5 and 10, right? So this is the heap sort code example, and you can try this, and with any language you can try, right? And you can do something like heap sort analysis. So it works in O n log n in best case, average case and worst case, and in space complexity is O1. So but it's not stable, right? And also when we talk about the advantages, so it has a guaranteed O n log n performance, you can see from this, right? And in place sorting, so there's no extra memory needed, right? And also excellent for unordered data set, right? And also the disadvantages, we can say it is not stable and slower than the quick sort in practice, and it has poor cache performance. And when to use heap sort? When guaranteed O n log n performance is needed, and when memory is limited, when worst case matters, you can use heap sort, right?